Okay, welcome everybody to the virtual time series seminar. It's my great pleasure today to introduce our speaker, James Duffy from Oxford, who will speak to us about common trends and long-run identification in nonlinear structural VARs. He's joined by our guest panelist, Peter Boswijk from Amsterdam. Thank you both for accepting our invitation. And James, the floor is yours. Please go ahead.
Okay, thank you very much, Vijay. Yeah, I'm going to talk about common trends in long-run identification in nonlinear structural VARs. And this work is joint with my colleague Sophocles. And in this paper, we're going to be interested in some very broad questions about how we can, in a nonlinear structural VAR framework, reconcile nonlinearity and common trends, uh, how we can accommodate linear and nonlinear forms of co-integration within the framework of a VAR, and how we can also use the structure of a model, of a nonlinear model that admits co-integration to generate useful long-run identifying restrictions. And it may surprise you if you're familiar with the rather voluminous literatures that now exist on nonlinear VARs and nonlinear co-integration, that this problem of actually reconciling co-integration and nonlinearity in a structural VAR, and particularly reconciling nonlinear co-integration and nonlinearity in a structural VAR, this is still a long-standing open problem, as is discussed in this recent review of the literature on nonlinear co-integration by Chostine. So before I get into a discussion of how we're going to answer these questions in this paper, I first wanted to provide some motivation, explain how we got interested in these broad questions to begin with. And the starting point for this research came from thinking about series that behave as though they have stochastic trends, but which are also subject to some form of nonlinearity. And a leading example of this is provided by short-term nominal interest rate series. So here you see the federal funds rate in the US and the overnight interbank rate for the UK. Both of these series exhibit the kind of random wandering that's characteristic of a stochastic trend. But in recent periods, we also see significant epochs where these series have been at or near the zero lower bound. So there's a kind of nonlinearity that these series are subject to. We want to be able to model this kind of behavior. We want to be able to generate trajectories of this kind within the framework of something like a structural VAR. We want to be able to generate this series of zeros, for example, which you're not going to be able to get with any reasonable probability in a linear model. So our starting point for thinking about that was a class of endogenous regime switching models that have been very recently developed, also with a zero lower bound as their motivation. So a leading example of a leading instance of these models is provided by this censored and kinked structural VAR model, which comes from one of Sophocles' recent papers. Now, this is a VAR in P variables. P minus one of those variables enter linearly through X and as X, and one of those variables, YT, which is a scalar, it's allowed to enter non-linearly. In this case, it's allowed to enter with coefficients which differ according to whether YT is above or below a threshold, which here I'm just normalizing to zero. So both YT on the left-hand side and its lags enter in this nonlinear way, or equivalently, the positive and negative parts of YT and their lags enter with different coefficients in this model. So this is a system of P equations, so each of phi plus 0 and phi minus 0 are vectors of P coefficients. And so this is the model in Sophocles' paper. And it's also the case that if you look at the paper by these four authors, who are interested in modeling occasionally binding constraints, they start off from quite a different starting point from Sophocles, but after making some assumptions on their model, they end up with a model that's very similar to this one. Now, how would one apply this to kinds of interest rate series that we saw previously? Well, you might include interest rates as one of, along with, say, inflation and unemployment. Those could go in the vector X. The interest rate, well, YT here would be a variable that represents the stance of monetary policy. The positive part of YT would be the actual observed policy rate, which would be constrained to be non-negative, of course. And when the zero lower bound constraint is binding, so Y itself becomes negative, the negative part of YT would represent the shadow rate, a kind of measure of what unconventional policy is doing when the actual policy rate is at zero. So these models treat something like the zero lower bound, that occasionally binding constraint, as a kind of endogenous regime switching, that the model, the series evolve according to one linear VAR when YT plus and its lags are all positive, and they evolve according to a different VAR with different coefficients when YT and its lags are all negative. And so this was our starting point, was the analysis of this model. We were interested in conditions for stationarity in this model. We quickly found that if we tried to verify those conditions on the kinds of data sets that you might apply this to, so series on short-term interest rates and inflation and unemployment, for example, those conditions on for stationarity were very unlikely to be satisfied. So we became interested in how could we accommodate stochastic trends in this nonlinear VAR framework. And so in a recent paper with Sophocles and a former undergraduate student of mine, Sam Wycherley, we gave a complete characterization of common trends and linear and nonlinear cointegration in this model. That's just representation theory. We have a bit on inference in a paper with Anna Bikovskaya. I have some work on inference in the sort of special dynamic Tobit univariate case of this model, which only involves YT. Okay, so we're going to take this model as our starting point, basically, and we're going to generalize this now in order to answer these three broad questions that I posed on the first slide. So in this paper, in this talk today, we're going to develop a more flexible class of nonlinear structural VAR models that will encompass the CKS VAR. We're going to, within that framework, extend the Granger-Johansson representation theorem from linear to our nonlinear structural VAR framework. And then on the basis of that, we're going to obtain a characterization of the directions in which shocks may have permanent or only transitory effects. And so the kinds of long-run identifying restrictions that are available in a co-integrated linear VAR will also become available in this nonlinear VAR with common trends. Okay, and finally, before I get to our answers to these questions, let me just say something about the literature that we're building upon. Of course, there are big literatures on nonlinear VAR models. I could easily fill the slide with references to that literature on vector threshold autoregressive models and smooth transition autoregressive models and so on and so forth. What I will say about that literature is it's been almost exclusively concerned with modeling stationary series through linear time series models. So it has sought conditions for stationarity in these nonlinear models. And so for the most part, we'll have to take a different approach to what's been taken in that literature to understand the behavior of the model I discussed today. There are some technical tools that we can borrow from that literature, though, in particular, this paper by Liebscher, which uses conditions on the joint spectral radius of a collection of matrices to control the dynamics of a nonlinear system. We'll also be able to use that approach to control the behavior of the equilibrium error components in our co-integrated nonlinear VAR. Another related literature, of course, is the literature on the Granger-Hansen representation theorem, which goes back to the very dawn of the development of co-integration theory. And this is a literature that's recently received some renewed impetus from, in particular, from Brendan Bear and his collaborators, who have worked on extending this theory from a finite dimensional case to the case of Hilbert space-valued processes. And allied with that representation theory, there's, of course, literature now, big empirical literature in macroeconomics that uses long-run identifying restrictions to help identify parameters of interest in co-integrated structural VARs. The first contribution along those lines, of course, was the famous paper by Blanchard and Coir. Moving on to literature on nonlinear co-integration more specifically, which is a bit more closely related to what I'm going to discuss today. One, I guess probably the closest literature to what I'm going to present today is this literature on nonlinear vector error correction models. This goes back to sort of a paper by Bork and Fomby. It's been subsequently elaborated in a way that culminated in some very nice papers by Sykinen and Christensen and Rabeck in particular. These are VAR models written in vector error correction form, in which we allow either the lagged differences or the equilibrium errors to enter the model non-linearly. So here you see a sort of prototypical example of one of the models used in that literature, where we've allowed the equilibrium errors. So beta here gives the co-integrating relations between ZT. We're allowing for a non-linear rather than a linear function of those equilibrium errors to enter on the right-hand side. So that literature has established conditions for stationarity of the differences in the equilibrium error components in those models. So there's a kind of Granger-Hansen representation theory that's been developed in that literature. The overlap between this literature and the models I'll discuss today, there's some overlap, but to a very large extent, you'll see the assumptions that we make do not really coincide with the assumptions made in this literature. And in particular, one feature of these models is that the co-integrating relations have to be linear. So there can be, in these models, there can be nonlinear dynamics in the short run, but in the long run, everything is described by linear common stochastic trends and linear co-integrating relations that kill off those common stochastic trends, whereas the models we'll discuss today will allow for the possibility of common stochastic trends entering series non-linearly, and therefore non-linear relations between those series being necessary to kill off those common stochastic trend components. Another branch of the literature on nonlinear co-integration takes as its starting point the triangular representation of a linearly co-integrated system, going back to these seminal papers by Park and Phillips in the early 90s, so the late 90s, early 2000s. And these are models where sort of you have a vector of linear I1 processes, xt, and yt, another component of the process, is modeled as a nonlinear function of xt plus some weakly dependent linear process. And the name of the game here is to estimate f either parametrically or non-parametrically. So there's a lot of literature here on the asymptotics of estimators of f. And this model, this kind of framework, unlike the framework in the first point, this is able to allow for long-run nonlinearity, a nonlinear relationship between two sort of stochastically trending processes in a sense. But this literature has never found a way of sort of relating this kind of long-run behavior back to a structural VAR framework in at least in a non-trivial way. And one thing that I find a bit uncomfortable about this, disconcerting about this framework, is that there's this inherent asymmetry in the treatment of yt and xt, in that one component has to be a linear process and the other is a nonlinear function of that linear process. So you can understand what we're doing today, in a sense, finding a way of capturing this kind of long-run nonlinearity within the framework of a VAR model. Okay, so the remainder of the talk is going to be organized as follows. I'm going to introduce our VAR framework and discuss sort of the identification problem in that structural VAR framework. Then I'll give the Granger-Johansson representation theorem within that framework. I'll first remind you of what this looks like in a linear structural VAR, in case you've forgotten, and then I'll give a fairly detailed discussion of our assumptions and what they yield in the first order case, and then just a brief discussion of what happens in the higher order case. I'll then move on to a discussion of the long-run identifying restrictions that are implied by that representation theorem. I'll give a brief illustration of sort of the trajectories that you can generate with this kind of model in the three regime VAR. And if time permits, I'll give a brief discussion of how the theory we develop here can be applied to a paper that's very recently appeared in the empirical macro literature that looks at the possibility of a long-run nonlinear relationship between potential output and inflation, a so-called long-run Phillips curve relationship. Okay, so what is our framework? Well, start with a p-dimensional linear structural VAR. So Z here is a p-dimensional vector, and each instance of ZT and its lags is being transformed linearly by a linear function encoded by these phi matrices. And what we're going to do is to take those linear functions and replace them by general nonlinear functions which map to p-dimensional space. So both up here and down here, there are p equations. Each ZT is being mapped. ZT is being mapped by F0 into p-dimensional space. ZT minus I is being mapped by Fi into p-dimensional space. And the one thing that we are going to retain from the linear VAR is the separability across time. So each of these functions is acting only on one lag of ZT. Okay, now why have we extended the model in this direction? Well, we wanted to do this in a way that allowed us to retain some tractability, and I'll explain why in particular this time separability is very important as we go on. We also wanted to be able to capture the CKS VAR, which was our starting point. Well, that can be accommodated within this framework very easily by recognizing that that is a form of this model where each of the Fi functions have this piecewise linear form. So as one of the variables, one of the components of Z, call it Y, changes sign, the coefficients on Y change, so you get a switch between these two different regimes corresponding to these two-order regressive matrices. Okay, so this is a direct generalization of that model. Okay, so that's the framework the rest of the paper is going to be, the rest of the talk is going to be proceeding within. And I want to say also something about the nature of the identification problem in this framework. So just as I would in a linear VAR, I want to say that there is some underlying sequence of structural shocks, which I'll denote by epsilon, which generate ZT. So that there is some parameterization of this model. And in this setting, a parameterization consists of an intercept and a collection of these nonlinear functions Fi. There is some choice for those functions which allows me to write ZT in terms of this underlying sequence of structural shocks epsilon t. And So each of these structural shocks correspond to things that have a definite economic interpretation. So maybe the first component of epsilon is a monetary policy shock, second component is an aggregate demand shock, and so on and so forth. So we take this up here as the truth. I should say that epsilon is, the components of epsilon are assumed to be uncorrelated, normalized to have variance unity, means zero. So I've got an identity covariance matrix here. I'm also going to assume that the epsilons are independent through time. So the components of epsilon need not be independent of each other. They just have to be orthogonal, but I'm assuming that the epsilons are IID through time. Okay, so this is the truth at the top. And it may well be the case that we can find another parameterization of the model, which allows us to write ZT in terms of some other IID sequence of shocks, which also have mean zero and identity covariance matrix. We know from the linear model that there are usually many different representations for ZT in terms of some IID shock vector with identity covariance matrix. So the question we are interested in then is, when are these two possible representations for ZT observationally equivalent? Well, if the parameters of these models combined with the density of the error processes, of course, if they imply the same conditional density for ZT given its lags. And we have a characterization, of course, of observational equivalence in a linear structural VAR. Two parameterizations of a linear structural VAR are equivalent if they're related by some orthogonal rotation matrix. Well, we can show that the same characterization of observational equivalence is available in our setting under certain conditions. So under conditions which are given in Appendix A of the paper, we can show that these two representations for ZT will be observationally equivalent if and only if there is an orthogonal matrix that links the FIs down here to the FI epsilons up here. So in a sense, ZT informs us about the parameters of this model up to some unknown orthogonal matrix epsilon. So in a sense, we face the same problem, despite the fact that the parameter space for this model is much richer than a linear VAR. We face the same identification problem as we do in a linear VAR. So that the data tells us about everything except for this orthogonal matrix. And in order to recover things like structural impulse response functions, we're going to need to introduce some additional restrictions to pin down this unknown orthogonal matrix. I won't here digress by going through what these conditions are that we need for this characterization to hold. Suffice to say, we need to have some sufficient dependence of the right-hand side on the lagged variables. For example, if all of these lags here was zero on the right-hand side, then it would be the case that F0, the function on the left-hand side, could not possibly be identified in any meaningful sense. So our conditions relate to the right-hand side here. Okay. So,
James, can I briefly ask a question?
Yes.
Yes. If you're interested in observational equivalence, then I would imagine that the two densities rho and rho epsilon also have to be related in an obvious fashion, right? So I can see that those are not the interesting parts, perhaps, of the dynamics, but they seem to be missing from my perspective, basically from these conditions for observation equivalence. But
yes, so that's a good point. So the way that the result is phrased, and this is borrowing from a result of Matsken's on identification in nonlinear simultaneous equations models, is that if you give me the parameters down here, C and the Fs, the question is there a density for the errors ut that renders it observationally equivalent to what's up here. And that will be the case if there is an orthogonal matrix linking these things.
Thanks.
Okay, so let me go on to the Brown-Johansson representation theory in this setting. Now, firstly, in a linear, let me remind you what this looks like in a linear structural VAR. So here we have our linear structural VAR, and the more compact representation of that in terms of an autoregressive polynomial. We can equivalently write the system in this way in terms of as a vector error correction system. And let me remind you what the conditions we need in order to generate co-integrated I1 series in this model are. The first condition is that phi 0 should be invertible. Often this theory is stated when phi 0 is the identity, so this is automatic. We need a condition on the rank of the autoregressive polynomial at unity. It should have rank R less than P. Say R is equal to P minus Q. P, remember, is the dimension of the system, the dimension of Z. And as a consequence of that, we can factorize phi at unity, or equivalently the pi matrix that appears on the right-hand side of the vector error correction representation as the outer product of two rank R matrices, alpha and beta. You will remember that beta carries the co-integrating relations between ZT. The third condition, and there are many equivalent ways of expressing this, one way is as a condition on the autoregressive roots of the autoregressive polynomial, that it should have Q roots at unity and all the other roots should be stationary. So importantly, to get I1 series, we need the Qs that appear in these two conditions to be the same thing, to coincide. And a consequence of that theory, a consequence of those three assumptions is that we obtain a representation for ZT in terms of Q common stochastic trends. So here we have highlighted the partial sum process of the UTs. So they're P random walks here, but they're being pre-multiplied by a rank Q matrix. Now, alpha and beta perp are the alpha perp and beta perp are the rank Q matrices that are orthogonal, whose columns are orthogonal to alpha and beta respectively. So this is a rank Q matrix here. We have Q common trends. We also have a stationary component given by VT here, and some initial conditions. And what does this look like graphically? Well, okay, the first thing to note is this decomposition tells us something about the long run effects, the permanent effects that a shock can have, insofar as shocks will enter the right-hand side in two ways. One way is through the stationary component on the right-hand side, but because that's stationary, the effect of the shock will decay as the time horizon runs out to infinity, whereas the highlighted term accumulates all the past shocks. So a shock in period one can have a permanent effect through this first term, so long as it doesn't get killed off by alpha perp transpose. So shocks that happen to be in the directions that are killed off by alpha perp, equivalently in the direction spanned by alpha, will have no permanent effects. So there's going to be an R-dimensional subspace along which shocks will have no permanent effects. And this has been a fruitful source of long-run identifying restrictions in a structural VAR, as I'll discuss a bit later. Graphically, what does the behavior of the system like this look like? Well, here I've just rigged up a very simple bivariate first order example where the co-integrating relation is minus 1,3/2. So it's given by this vector here. And a consequence of this is that the components of Z1 and Z2 will move in such a way that Z1 moves sort of 3 on 2 for every 1 unit movement in Z2. So we get trajectories that look like this. And what's going on is that although a shock can take Z1 and Z2 to any part of two-dimensional space, they will tend to be attracted back towards this blue line on the left panel. So they will, whenever a shock takes them out of equilibrium, they will tend to return to some point on this blue line until they're hit by another shock. And indeed, the adjustment towards equilibrium will occur along the subspace spanned by alpha. So if we're initially in equilibrium, we're hit by a shock, then we just have to find, in order to determine what point we end up converging back to, we just have to find the affine translation of span alpha that passes through this point that we've been moved to, and then we move along that back to the equilibrium. And so this is representing again the fact that impulses that are in the direction of span alpha will have no permanent effect. The other reason why this theorem is useful, of course, is that it tells us something about the long-run behavior of the standardized process generated by the model, and this is vital for asymptotic inference. This is also going to be the case in our nonlinear model, but I'm not going to have time to discuss inference today. But this is also one of the reasons for deriving a theorem like this in our setting. Okay, so let's move on to the nonlinear VAR one now. Okay, so the first step is, just as in the linear case, we need to find a kind of vector error correction representation of this system that will allow us to isolate the sort of stochastic trend and weakly dependent components of the system in some sense. And here is a point at which the additive time separability becomes very useful, because we can obtain a kind of VECM representation here. So let's say I have a second order system, so just two lags of ZT on the right-hand side. I will subtract F0 of ZT minus 1 from both sides, so I get a time difference of F0 of ZT on the left-hand side. And then I'm going to add and subtract F2 of ZT minus 1 from the right-hand side. And just, you will see that now I have a collection of functions of ZT minus 1 and a time difference of a certain nonlinear function of ZT minus 1. So I'm going to call that function of ZT minus 1 pi, and what is minus F2, I'm going to call G1. So I've got the time difference of G1 of ZT minus 1 also appearing on the right-hand side. And this approach works more generally. So in the kth order case, I get this kind of representation of delta F0 ZT in terms of a function pi of ZT minus 1 and some time differences of nonlinear functions of lags of ZT minus of ZT. The important thing here is this function pi. This is going to play the same role that the matrix pi did in a linear co-integrated system. In particular, we're going to have to make an assumption on pi, which is going to be comparable in its effect to the rank condition that's made in the linear version of the Granger-Hanson representation there. Okay, so now we have all the ingredients to actually give what our conditions are in the first order case. So here is our first order VAR, and it has this trivial vector error correction form. And so our first condition is going to be comparable to the invertibility condition on phi 0, which is that F0, the function F0 should be invertible, and will also require something which is automatic in the linear case, that it be continuous and its inverse be continuous. So it's a homeomorphism. The second condition, this is our counterpart of the rank condition. This relates to the nonlinear function pi now. This is, the condition is going to be that pi of z, this nonlinear function, should be representable in the following way as the product of a Rankar matrix alpha times some potentially nonlinear function theta, which maps from p-dimensional to r-dimensional space. And then, so that's our rank condition. Our condition on that's analogous to the condition on the roots of the autoregressive polynomial in a linear system. This condition admittedly looks a bit complicated when you first see it. Now, hopefully it will become clearer in the next few slides. For the time being, I want you to think about this as being a condition on the gradients in a certain sense of this function theta. And so if I take any two values, z and z prime in p-dimensional space, I can always find some matrix beta that will relate the difference in the function values to the difference in the arguments. Okay, there'll be some beta that will make this equation hold. And I'm going to require that whenever I compute, try and solve this equation for some beta, that I should be able to find a beta lying in some compact set script B. And in fact, requiring this set of gradients, as it were, script B, to be compact, this is equivalent to requiring theta to be Lipschitz continuous. Of course, if theta were linear and equal to beta transpose Z, then there would just be one beta here. Things would simplify a lot. Now, my condition on these gradients is not so much compactness, which, as I said, that's just equivalent to Lipschitz continuity. It's a condition on these matrices that are highlighted here, formed from the identity plus beta transpose alpha. We're going to require that this collection of matrices formed as beta ranges over this set of gradients, this has joint spectral radius less than 1. So not only do the individual matrices have spectral radius less than 1, but collectively, in some sense, they have spectral radius less than 1. I'll discuss what is meant by the joint spectral radius in a few slides. Consequence of these three conditions is that this process xi t, defined as theta of zt, so this will play the role of the equilibrium errors in our system. It won't be stable, it won't be stationary necessarily, but it will be stable in a sense I'll define shortly. It will be guaranteed to be of smaller order than any stochastic trend. So it'll be sort of stochastically bounded in some sense. It'll be, in fact, dominated in a certain sense by a stationary linear process. So these equilibrium errors are what we call stable, and there exists a homeomorphism, a nonlinear, potentially nonlinear map chi that allows me to express zt as a nonlinear function, chi inverse, of an initial condition, a set of q common stochastic trends, and a stable equilibrium error process. So we get exactly the same kind of decomposition here as we get in a linear structural VAR, which is co-integrated. Okay, and let me say now something to sort of cast some light on these conditions, what each of these conditions is actually doing for us. So the first condition, this is to help us deal with the fact that we have F0 of ZT on the left-hand side, which makes the analysis of the system rather more cumbersome than would be the case if we just had ZT on the left-hand side. Well, the idea is to use the fact that F0 is a homeomorphism to define transformed variables, ZT star as F0 of ZT, and rewrite the system in terms of these transformed variables. So we end up with ZT star being equal to F1 of ZT minus 1 plus UT. We can apply F0 and its inverse inside F1 to rewrite the right-hand side in terms of ZT minus 1 star being transformed by F1 compose F0 inverse. And then we just define a function F1 star to be F1 composed with F0 inverse. And we obtain a new system in these transformed variables, which has the great virtue of having a trivial left-hand side. The identity is the left function appears on the left-hand side now. So this essentially says we can focus on the simpler case where F0 is the identity. Okay, because we can always solve the problem for the transform variables and then just at the final step, go back to the original variables by applying the inverse of F0. Okay, what about this second condition, our counterpart of the rank condition, this condition of the factorization of pi? Why is that condition useful? Well, let's go back to our VecM type representation of the first order system and introduce that condition. One of the key steps in the proof is going to be extracting the common stochastic trends that are driving ZT. And this gives us a way of doing this because we can kill off the dependence of the right-hand side on ZT minus 1 just by multiplying through by the orthogonal complement of alpha, multiplying through by alpha perp transpose. And we're just left with the errors on the right-hand side and this time difference of F0 of ZT. And then we can sum up this over all the periods from period 0 to period T. The sum on the left-hand side telescopes, and we're left with a representation for alpha perp of F0 of ZT in terms of initial conditions and Q common stochastic trends. So in this first order case, we can very straightforwardly, of course, this will be more complicated in the higher order case, but here we can very straightforwardly define a map which extracts those Q common trends from ZT as just alpha perp transpose times F0 of Z. Okay, so that will give us, that sort of gets us halfway to the representation theorem because this gets us a way of extracting the common trends. The other thing we have to do is to show that there are certain function of the series, a certain r-dimensional function of the series that will behave like a stationary process. The equilibrium errors in the system will be stationary. And let me just, for the purpose of discussing, so that's what's delivered by our third condition. For the purposes of discussing that, let me just suppose we're in the case where F0 is the identity. So here is our even simpler first order system written in vector error correction form. And we're going to define theta of ZT minus 1 to be xi t minus 1. These are the equilibrium errors in the system. In a linear system, I would have beta transpose ZT minus 1, right? There'd be the linear co-integrating equilibrium errors. And I want those equilibrium errors to be of smaller order than the common stochastic trends. Well, to do that, I need to obtain some kind of order regressive representation for xi t. How am I going to do that? Well, I need to relate, I've got xi t minus 1 on the right-hand side here. I need to relate the delta zt on the left-hand side to delta xi t on the right-hand, delta xi t in some way. So this is where the third condition comes in, because delta xi t is just the time difference of theta of zt. And remember, I can find some matrix of gradients from that set script B, which ensures this second equality holds here. So it allows me to relate the difference of theta zt and theta zt minus 1 to delta zt. Now, of course, beta t is going to depend on zt and zt minus 1, but we know that it has to come from this set script B. So we obtain in this way a time-varying order regressive representation for xi t. Now, in general, this is not going to be a stationary process because the model allows for beta t to depend on the level of zt, which is a stochastically trending process. But there are going to be cases in which this will turn out to be stationary. Of course, if we go back to the linear model where there is only one gradient beta, then this just becomes a stationary, no longer time varying order regressive system. So we want to show in the more general case where beta t can be time varying because it can be drawn from this set script B of gradients, we want to show that it is, behaves like a stationary process in the sense of being stochastically bounded. In order to do that, to prevent it from exploding, we need to be able to control successive products of these autoregressive matrices, which will be of this form, where these betas come from script B. If we have a linear model, of course, we've only got one matrix appearing in these products. We would just need that matrix to have spectral radius strictly less than 1, which would be the condition implied by the root condition in the linear version of the Grange-Hanson representation theorem. Here we need to control these matrix products, and that's exactly the control that's delivered by a condition on the joint spectral radius of these matrices. So the joint spectral radius of a bounded set of matrices, this provides a bound on, in a sense, on the products of arbitrary length that one can form from matrices in A. So on the right-hand side of this expression here, you see the teeth root of the spectral radius of B, where B is formed from T-fold products of matrices in script A. So to say in particular that the joint spectral radius of this collection of matrices is strictly less than 1 is like saying that the spectral radius of all products that can be formed from that set of matrices must also be less than 1. And some important consequences of that condition are that if we have a dynamical system like this, for example, where we have a time-varying autoregressive matrix that comes from some bounded set of matrices script A, if that set of matrices has joint spectral radius strictly less than 1, if we have a deterministic system with no shocks, then we have convergence of WT to 0 from any initialization. If instead we have shocks, but we have certain bounds on their moments, then we can also get corresponding bounds on the moments of WT, or bounds, for example, on the maximum of WT. So 2 plus delta moments for VT would ensure that WT is of strictly smaller order than a stochastic trend. So this is a condition that's been exploited in previous work on stationary nonlinear autoregressive models to establish ergodicity. And there's also some literature on computing approximate upper bounds for this quantity, and it can't be feasibly computed exactly, but there is a literature on computing upper bounds for this in the real world settings. So that is our third condition, is going to ensure that these autoregressive matrices that appear in this representation for xi-t have joint spectral radius strictly less than 1, and as a consequence, xi-t is going to behave essentially like a stationary, well, it's going to be dominated by a stationary linear process. It's going to be stochastically bounded, smaller than in magnitude than a stochastic trend. This condition I've given to you is stated for the case when F0 is the identity. If it's not the identity, we just have to amend it by replacing theta by theta composed with F0 inverse. And it turns out this is the only other condition. These are the only conditions that we need. So what we've shown now is that we've got a map psi that extracts the Q common trends from ZT, and a map theta of ZT, which gives us our sort of weakly dependent components. And the last thing we need to do, because we have a representation for chi of ZT in terms of initial conditions, common trends, and an equilibrium error process, the last thing we need to do is to invert chi to get a representation for ZT. And the remarkable thing is that the conditions that we've made ensure that this map chi is in fact a homeomorphism. So we don't need any further assumptions in order to be able to invert chi. and obtain a representation for ZT as a nonlinear function of initial conditions, few common stochastic trends, and these equilibrium errors. Okay, so very briefly, let me say something about the general case here. The result in the higher order case will be proved by a kind of companion form argument. Our condition on F0 being a homeomorphism and our condition on the factorization of pi remain exactly the same as before. The only condition that has to take an augmented form is that third condition, our analog of the root condition, because we have to control the higher order dynamics that are embedded in these functions GI. The one thing I will say here is that if you specialize this model to a linear model, then our conditions reduce to exactly the conditions required by the linear version of the Granger-Johansson representation theorem. So in this case, our conditions don't seem to be conservative in any way. And the representation we obtain for ZT is strictly analogous. We have a nonlinear function of ZT is a nonlinear function of initial conditions, few common stochastic trends, and this stable equilibrium error process, which again is of smaller order than those stochastic trends. Okay, it's the only real difference here is that chi now takes a more elaborate form because we have to extract the common trends using a slightly different function. Okay, so let me say something about the long-run identifying restrictions that we get on the basis of this result. So I'm going to try and elicit what the long-run effect of a shock could be without having the complications, too many of the complications posed by nonlinearity and stochastic trends. I'm going to run the following thought experiment where I fix the state of the model at some time tau and allow one final shock to hit the model at time tau, which I'll denote by u, and ask what's the limit of the process then as time runs out to infinity in the absence of further shocks. Well, I'm going to have a representation for ZT in terms of the state at time tau minus 1, the intervening shocks, and this stable equilibrium error process. As time runs to infinity, that equilibrium error process will go to 0 in the absence of further shocks. So the only thing that's going to, the limit is going to depend on is the initial state and those final shock vector ut, final shock vector u. So I converge to something which is a steady state solution to the model. What are the steady state solutions to the model characterized by? Well, if I look at the vector error correction representation, I see that for something to be a steady state solution, all the values of ZT and its recent lags have to be the same. So these time differences on the left and the right have to drop out. And so the only steady state solutions are given by the kernel of pi, right? Or equivalently, the kernel of theta. So I'm going to converge to some steady state solution. And the thing I want to ask is then, well, which shocks will have no permanent effects in this model is the shocks that would lead me to converge to the same point as if there had been no shock at all. And we look at the way that that final shock enters into the limit. Well, it enters multiplied by alpha perp transpose. So just as in the linear model, any shock that's in the direction spanned by alpha will have no permanent effect. So we obtain, in this way, same sort of long-run identifying restrictions that we do in a linear co-integrated structural VAR. Because remember, the thing that we don't know from the data is the mapping between the structural shocks and the shocks ut in some observationally equivalent representation of ZT. If we say partition the structural shocks so that, say, the first R of those structural shocks only have transitory effects, then it has to be the case that when those first R structural shocks are transformed via the operation of epsilon into U, they have to be pushed into the span of alpha. So it has to be the case that the corresponding columns of epsilon, those first R columns, live in the span of alpha. They're killed off by alpha perp. So this kind of reasoning gives us a collection of QR long-run identifying restrictions in the same way that we would obtain in a linear structural VAR. Okay, so let me show you now, just give you a little bit of an idea of sorts of trajectories that one could generate with a model of this kind. I'll give you a very simple example where we specialize the model to the case where these FI functions are piecewise affine. So you can think of them as sort of having L regimes determined by the value of Z. Within each regime there, we have an affine function. And I'll give you a very elementary example of a system falling into our framework where there are three regimes which are determined by whether or not the second component of Z, so Z is going to be a two-dimensional process. The three regimes are determined by whether the second element of Z is either less than -1, between -1 and 1, or greater than 1. And we will have, as it were, a co-integrating rank of 1 within each of those regimes, but with potentially different co-integrating vectors within each of those regimes, across those regimes. So in the example depicted here, we have this choice for alpha, and we have three different co-integrating vectors. In the regime corresponding to Z2 being less than 1, the co-integrating vector is -1/2, 1. In the inner regime, it's -1/2, 1/2. And then in the top regime, Z2 being greater than 1, it's again -1/2, 1. It doesn't have to be the same as in the bottom regime, but I'll just make it here the same for simplicity here. And you see the sorts of trajectories generated by this process such that Z1 and Z2 tend to move 1 for 1 when Z2 is inside this threshold, but 2 for 1 outside this threshold, outside this band. And in terms of the dynamics of adjustment back towards equilibrium, well, if I'm initially in equilibrium, the shock takes me out of equilibrium. Again, the adjustment will still be, in this first order case anyway, along the span, along a subspace parallel to the span of alpha. So shock will only have a permanent effect here to the extent that the shock was not in the direction spanned by alpha. Okay. So, Majid, how am I doing for time? Should I wrap up there, or is there time for
a few more minutes
more slides?
if you could wrap up? But there's time for the application, I think.
Okay,
Please go ahead.
thanks. So I'll just very briefly give an illustration of what this looks like in a real-world example taken from very recent empirical literature. So this paper by Ascari, Bonamolo, and Hack, they consider the possibility of a long-run Phillips curve relationship, a non-trivial long-run relationship between potential output and trend inflation. They do that by formulating a structural model in state space form with time-varying long-run components. So long-run inflation follows a random walk. Long-run output, so long-run output y bar, this is equal to potential output y star plus a nonlinear function delta of inflation, delta pi t bar, okay, of long-run inflation rather. And yt star, potential output, this is modeled as an I2 process. Okay, and okay, their observed series are modeled as transitory deviations from these long-run components. I'm not going to worry about the observed series here. What I want to say is how can we use our framework to say something about what the implied behavior of these long-run components is. So I'm going to rewrite this system as a 3-equation VAR, because you'll note there are only 3 shocks here. So I'm going to effectively take out potential output y star here. So I have an equation for inflation, an equation that involves the growth rate of long-run output, and G is the growth rate of potential output. So this model doesn't fall into the framework offered by any existing literature because we have this nonlinear function of a stochastically trending process appearing in the second equation of the VAR. So what we can do, however, is we can fit it within our framework as a first order nonlinear VAR. So with F0 collecting the objects on the left-hand side here, F1 collecting the functions of the state vector on the right-hand side. And if we want to understand the long-run behavior of this, we just have to first compute what pi is. Remember, that carries the information about the co-integrating relations in this system, as pi is F1 minus F0 here. So things are very simple here. It factorizes as alpha being this matrix, this vector 0, 1, 0, and the co-integrating relations here are just linear. It's just a co-integration between G and so the growth rate of potential output and the growth rate of the long-run component of output. And we also know from our results how to extract the common trends in this system as alpha perp transpose times F0. Well, we know what alpha is, so we just take something that's whose columns are orthogonal to it, and we can extract the common trends just as by extracting the first and third components from Z. And so applying our theory, we can obtain a representation for Z, this three-element vector, in terms of a function chi of two common stochastic trends and an equilibrium error process. Pi here is going to be a linear map. So whereas the nonlinearity in the system gone, well, the nonlinearity has gone into xi in this case. Xi will exhibit these nonlinear, non-stationary dynamics, but it will be guaranteed to be of smaller order than the stochastic trends. So we have a system, despite the nonlinearity that appears in these equations, with a linear co-integrating relation and two common stochastic trends driven by the shocks to long-run inflation and long-run growth. Okay, so to conclude, we have developed a flexible class of nonlinear structural VARs, extended the Granger-Johansson representation theory to this setting, and obtained long-run identifying conditions analogous to those available in a linear co-integrated structural VAR. And the next step, one of the next steps in this research will be to use that representation theory to derive limit theory for the processes generated by this model, and thence to develop results for frequentist inference in this setting.
Wonderful. Thank you so much, James. That was wonderful. Let me stop the recording.